So welcome back to next session, students. So here we are going to discuss the film sensors. Film sensors. So these are the topics we have completed so far, and we discuss film sensor in this session, and two more topics left out: MEMS and nano sensors, laser sensors, that we will discuss in coming sessions. So film sensor, basically such sensors are produced by film deposition of different thickness on appropriate substrates. The deposition techniques used are different for thick and thin films. So we are going to see thick as well as thin films. Sensors produced through these techniques have varying electrical and mechanical properties while a variable is being sensed. So first one is thick film sensors. Thick film deposition is a mature technique, and this there has there has not been a substantial improvement whilst thin films are being developed almost at some same pace as microelectronics incorporating latest technology. It is to be noted that thick films processes had been in use for producing capacitor, resistor, and conductors, and has subsequently been adopted in sensor development. So film sensor is explained here. The step one, selection and preparation of substrate. In steps two, preparation of the initial coating material is in paste or paint form. Paste or painting the substrate by coating material or screen printing it. Next is firing the sample produced in step 3 as an oxidizing atmosphere at a program temperature format. So these are the steps involved in making film sensors. The substrates used for developing thick film over them are alumina 96 or 99.5 and beryllia, that is 99.5 percentage. So there are fired at about 625 degrees Celsius. Others used are enameled steel, which is low carbon steel coated with low alkali content glass that fit that are fired at around 850 degrees Celsius. So this is about steps and substrates. So here the alumina or beryllia have dielectric constants around 9.5 and 7 respectively, with the dielectric strength around 5600 volts per micrometer. Thermal expansion coefficients are 6.5 into 10 to the power of minus 6 and 7.5 into 10 to the power of minus 6, respectively, with bulk resistivity being almost the same for both at about 10 to the power of 14 ohms centimeters. So thermal conductivities are 0.36 and 2.5 watts respectively. So enameled steels have better strength and machinability, being almost double for those of aluminum or beryllia, which have values around 175 megapascals. So through it has a better machinability and improved thermal conductivity. Enamel steel is less costlier also. For thin film deposition, alumina and beryllia can also be used. Besides, special glass quartz, fused silica, and sapphire are often used, which have similar properties and sometimes even better. So it is to understood that the compatibility between substrate and transducing element is thin film sensors is very important. For example, there should not be difference of thermal expansion coefficients, which would induce stress between them and correspondingly result in zero offset drift and instability. Sensors which are produced through thick film deposition, approximately 20 micrometers, are used for sensing temperature, pressure, gas concentration, and humidity. The first one, temperature. Thick film sensors such as thermopiles, usually gold and gold platinum alloy, thermistors, usually with oxides of manganese, ruthenium, and cobalt. And temperature dependent resistances based on gold, platinum and nickel are used for temperature sensing. So next one is pressure. Sensing pressure is possibly by making thick film diaphragms or capacitive devices made with aluminum Al2O3 and Bi2Ru2O7 are piezoresistive devices made of same materials. So these are film sensors are also playing major role in measuring the parameters like temperature, pressure, humidity, etc. So here selectivity is obtained by a second firing process at almost the same temperature by adding different ingredients for different gases. For H2 detection, for example, it is mixed with rhodium 6% by weight and fixed for 1 hour at 800 degree Celsius. For CO, THO2 thorium is added 5% by weight, and for NH3 zirconium oxide is added 5% by weight and processed in the same manner as done earlier. For control of the uh, porosity of the films, which determine the overall sensor sensitivity, organic materials are added in a selective manner. For example, alcohol is added for H2 and sometimes inorganic materials work well with appropriate selection. Silica of different varieties is added for CO and NH3. The materials so produced are now painted on the substrate and dried, then then uh, then continued at controlled temperature by varying times. The other thick film variety is the ceramic metal or cement, which consists of gold, silver, ruthenium, palladium based complex oxides, is an insulating medium. So mainly gases, that is glass, lead, borosilicate. So these are thick film resistors for the cement, which require precise control of heat treatment. The sensitivity is controlled by the size, concentration, and distribution of metallic component, that is, in their own resistive properties under the insulating medium. So that is the way how to make process the metals. And the pure metals, metal powders and resistors pigments differ in far as changes in their resistivity values are concerned, and hence their embedding in percent weight changes in resistivity of the sensor develop. So here this is one graph. So pigment by weight and resistivity ohms per ohms centimeter, and this is rhodonium oxide and Ag plus Pd, and this is AgAu, and by weight this is how it becomes for Ag it is like a straight line, and Ru's O2 it is like a curve, and for Au the weight is more, and also are the same resistivity. So this is a simple graph. And the thin next is thin film sensors. We are going to move to thin film sensors. So here thin film sensor processing differs from thick film technology mainly in the film deposition techniques. This technology is similar to that used in silicon micromechanism. A number of techniques are used for thin film deposition, such as thermal evaporation, resistivity heating, electron beam heating, the sputter deposition, DC with magnetron, and RF with the magnetron, chemical vapor deposition (CVD), plasma enhanced chemical vapor deposition (PECVD), metallo-organic deposition (MOD), and Lagmeyer blodgett technique for monolayer deposition. So these are the thin film sensor techniques, and we will see these techniques. So the PECVD processing system, you can see here, this is the gas in, and you have wafer kept here and the plasma kept here, and RF input is given here, and these are the AC electrodes. This one and this one are AC electrodes, and it is the RF input, and here this is the plasma is into pump. So there is the thermal expansion evaporation. The thermal evaporation and sputter deposition are decades old. However, the sputter is an improved form where a magnetic field perpendicular to the applied electric field is applied. So this increases the ionization probability of the electron as the Lorentz force E by B restricts the primary electrons near the cathode. As a result, sputtering efficiency is also enhanced. Plasma enhanced chemical vapor deposition has been found to be particularly suitable for sensor fabrication. This is a low temperature process in which plasma is introduced into the deposition chamber to enhance the pyrolytic process, which is normal CVD process, is performed by thermal decomposition that requires high temperature. So this is the PECVD, and to continue. So here the volatile compound of the material to be deposited is thus vaporized, decomposed and made to be deposited in thus vaporized, decomposed and made to react with gaseous species over a substrate to produce a non-volatile amorphous product on the surface of the substrate. The deposition level is controlled by controlling the flow rates of the vapors. A parallel plate radial flow type PECVD processing chamber was shown in earlier slide. We have seen that. The metallic organic deposition method MOD is another very versatile technique which can be used both for thick and thin film sensor fabrication. It consists of applying ink of a metallo-organic compound to the silicon substrate consisting silicon wafer coated with silica, then spilling the assembly at about 3000 rpm and finally heat treating the deposit. So metal organic compounds consist of central metal ion bonded with a ligand through a hetero bridge containing oxygen, sulfur, nitrogen, phosphorus, arsenic, and so on. It is prepared by dissolving the compound in organic solvent. So specifically prepared thin films by this technique are barium titanates, that is BaTiO3, and their derivatives that are mostly used for pyroelectric measurement, tin oxides for gas sensors, superconducting oxides such as yttrium, barium, copper oxides, YBAX, CuY, O2 for high temperature, and ZrO2 and TiO2 stabilized by yttrium for oxygen sensors. These film sensors measure the same variable as done by thick film counterparts with variations in principles and materials. Thin film sensors, the working principles of materials. The flow material is AU, so thermometry, and humidity Ta2O5, capacitance change, magnetic field NiS1 Fe19 NiCO2 CO72 Fe8 B20, magnetoresistive effect, oxygen ZnO, variation in electricity conductivity, and pressure, radiation, strain, and temperature. So these are the materials and principles used. So solid film generation of deposition on the substrate is done by a process known as dipping, which is a special mechanism that is either vertical or horizontal. However, orientation of the film on the substrate can be different with respect to hydrophilic or hydrophobic ends. So here, considering the circle end as hydrophilic and the line end as hydrophobic, three different orientations are obtained, which are shown in figures here. These are marked as XYZ, and here this is the uh, circle with end are shown here, circle with end, and these are the XYZ orientations, A, B, C respectively. So thin film sensors, LB films are good as ion selective membranes which deposited on the insulator face of the ion sensitive FET field effective transistor. Majority of LB films of different materials have found convenient use of biosensors. So LB gas sensors are classified as chemi-resistors and surface acoustic devices SAW. In the former, the change in conductivity of the sensor is related to the concentration of the gas, and the materials used for films uh, uh, are phthalocyanines and chlorines. Surface acoustic devices such as general SAW devices sense change in frequency due to absorption of gas by the film deposited on the piezoelectric substrate. Same materials can also be used for film deposition. So these are the film sensors, and there ends the film sensors, and we will move to next topic in next session. Thank you, students. These are the references you can rely on always, and these are the resources. So we stop here. We will move to next topic in next session. Thank you, students.